Well, good morning. This is 9:37 on Thursday, the 17th of November, 2016. We should be in differential equations right now, but right now I'm the only one in the room, so I'm in the differential equations class. Hopefully, someone else will be getting here, preferably all five, but right now there's 0. I'll take anybody. I was waiting for this to come up. We'll do the slideshow from here. All right. Again, sorry nobody's here. Just a couple of one thing to mention. Well, a couple things to mention. I guess you know already there are no classes next week. Okay, Thanksgiving week you have the entire week off. Okay, now. What to do with that week? Well, of this class, 5 students left in the class. Only 1 has turned in the paper, okay? So please, the other 4 of you get working on your paper, okay? And right now, the first test, only 1 person has turned in the first test. I haven't finished grading that yet, but I'm working on it. So, and we're very close to the time to have the second test. So please, folks, get your, I hope you take advantage of the time that you have and work on your exam, your test for chapters 1 and 2. We're now in chapter 4, and we are making decent progress toward 4. So please take advantage of the time you got to get those done. Now, we're on page 153, section 4.5, undetermined coefficients, the annihilator approach. And example 5 is similar to example 4, only we have a different equation. So let me get my pen activated here. And what we have is, example 5 is solve this differential equation, y double prime plus y is equal to x cosine x minus cosine x. Okay. Now, you start with the complementary function. That's the left-hand side, where you set that equal to 0. Okay? And our technique for that, rather than like the book just says what it is, I want to show you where to go to get it. Okay, it's back in 4.4, I believe. No, probably 4.3. Okay, 4.3. Second order differential equation. Okay. When you write this down, our first assumption is writing faster than I'm talking. Okay. Let y equal e to the mx. Okay. Yeah. Very top of page 133, you'll find this is where we usually begin, e to the mx. Okay. I was tempted to skip all this and go, but I think you always need to go back to that. Okay. Y prime then would be m e to the mx, and y double prime is equal to m squared e to the mx. Now, if you can avoid that, that's fine. Okay, and when you plug this into your left-hand side alone, you get m squared And I'm going to leave out the e to the mx because if it's equal to 0, that's never equal to 0. So, and this is your complementary equation. M squared plus 1 is equal to 0. And we know that's never the case in the real number system. But when we go to the complex number system, again, this is why I took you back to page 133. It's case 3 at the bottom of that page. Conjugate complex roots. Okay? And it goes to Euler's formula, and ultimately that leads to, this will be at the top of the next page, when you have a function like this, and of course your only solutions would be m is equal plus or minus I, right? Because subtract 1 from both sides and you have m squared is equal to minus 1. The only solution to that is m is equal plus or minus I. Okay. Now, when you have that as a solution, remember, and here's Euler's formula just for your memory, e to the I theta, okay? And by the way, this then would produce, this is why I went back and did this, e to the ix or e to the minus ix, okay? Now, what that's equal to, e to the ix would be cosine theta plus I sine theta. Okay, e to the minus ix would be cosine theta plus, or minus, sorry, I sine theta. Should be putting x's in there, sorry about that. Minus I sine x, sorry. Let me go back and change those thetas to x's. Okay. Now, your general rule from this is then because of their in conjugate pairs then, if you were to work through those, your y, and this is where they jump to in the other part, the y is equal to, and this is on page 134, C1, okay? Now, I guess there's one more thing we need to put here. The real solutions to this are e to the alpha x cosine beta x and e to the alpha x sine beta x, sorry about that. Okay, those are our two solutions. Now, what are the alpha and the beta? Okay, now, they just really do a poor job here. This is the beta, okay? I'm sorry. this is the beta. The okay. Let me correct that. It is true, but that's not the best place to go. Okay, sorry about that. Okay. Okay. When you have these as your two solutions, the beta is the coefficient of the x, okay? In this case, in both of these cases, beta is 1, okay? And what is the alpha in this case, okay? It's the, finally, okay, I had it buried in here. The alpha is the real part of the E. In this case, it's 0. Okay, so alpha is 0, and beta is the coefficient of your x. Okay, your M, you might say. Okay, except, I mean, you got the I in there too. So now you're using this as your general solution, that C1 e to the alpha x, well, your alpha is 0. So that's just going to be 1. Okay? And your beta is 1, so that's going to be C1 cosine x plus C2 sine x. Okay? Now, they took you through x's and thetas and everything else, but that's what it turns out being. Okay? C1, because you have no alpha. Alpha is 0, and your beta is 1. So that is your solution. Okay, sorry, it took me several iterations to get to the simplest form there. That's what you have. Once you have this, M is equal to I, this will be alpha plus beta I, okay? And your alpha here is 0, your beta here is 1. So that's where it would have been the easiest place to do it, okay? And so you don't need e to the I theta. That's going too far back, okay? Okay. Now, that's why they say, in example 5, they just say YC, this is a complementary solution, is C1 cosine x plus C2 sine x. I don't know what that dot is there for, but it's in the way. Okay. So there's your complementary solution. All right. Now, let's go to the specific or particular solution, and that is your this part. Okay. This part is your particular solution. Okay. And if this one, you go back to page 150, equation 7 there, and you note the annihilator operator that is going to deal with cosines, with x's, e to the x's, and cosines and sines. And here's what it is. Okay? For the first one, which is x cosine x, that annihilator is going to be, notice we don't have any E's in this one. Okay. You don't have any alphas here. Okay. You look at the x cosine x. There's no e to the alpha x here, so that means alpha has to be 0. There is one x e to the alpha x, with alpha being 0, and cosine beta x, but beta then would be 1. So then this would give you, for this one, your annihilator would be d2, and then your alpha is 0, so that's out of the picture, plus beta squared, which is 1. Okay? All right. Raised to the nth power, and n here is 1. N is the exponent of your variable. So this is your first annihilator. Okay? And that's where, and you notice that d squared plus 1. Okay? I'm sorry, it's squared, because your annihilator there is always, the power n is 1 greater than the exponent of x. And that has an exponent of 1, so your n here is n plus 1, is 2, okay? Is 1 plus 1 is 2, okay? So that gives you that one. Now, if you want to expand that out, you could, but I think it's better not to. Okay? Now, your second one, the minus cosine x, that has an annihilator of, and it doesn't matter about the sign there, just cosine x by itself is just, your n in that case is 1. Okay, because the x to the 0th power, so that gives you an n of 1. So that, and again, your alpha is 0, beta is 1. So the other one would be d squared plus 1 to the first power. Okay, so they have the same forms there. We will choose the maximum of those two. The annihilator for the right-hand side will just be that one, because you don't need to do a, you pick the one that's the lowest power that covers them all, and this covers both of those. So you don't need to worry about that one. Now, however, if you'll notice also what your original function was, it was, your annihilator is going to be the d squared plus 1. Okay. My pen is really, really slow. There we go. I don't know why it's so slow. But your original function is a d squared plus 1 as well. Oh, and this is a d squared plus 1. Your annihilator is with the second power plus 1 to the first power. That's from this right here. This is d squared, and this is plus 1. Okay. So that's from the original, okay. And that's all multiplied by y, or operating on y. They're not multiplied. These are operators on y, and that's now equal to 0. We're wanting to annihilate them, so that's what we want to happen. Okay. Well, this gives you a d squared plus 1 cubed. Y is equal to 0. There's the one there. My pen is so slow, that's why it's writing over itself. Okay. Now, okay. Now we do the auxiliary equation for this function, okay, with a cube there? Well, it looks like, and in fact it's going to be the case, that certainly this thing is going to have to be 0. D squared plus 1 cubed has got to be equal to 0. It's operating on 1, okay? Well, sorry about that. I said that poorly. Let me erase this. If you plug in and do your basically auxiliary equation for that one, and I hate to use it again, but just because we're used to using it, I'm going to use m, okay? So that's m squared plus 1. So again, this gives you back where we were before. M is equal to plus or minus I, but now those plus or, sorry, it keeps doing that. This is now a, those are both roots of this with multiplicity 3, because it's plus or minus I cubed, you know, so both of those have multiplicity of 3, okay? So your auxiliary equation becomes, more than the auxiliary equation, it would be y is equal to, now, this thing is so aggravating, okay? Skip the other part. I don't know why they put it in now. It's really not necessary. Just do the particular solution. Okay? Now, what does that lead to? You have, and if you go back a page, your n is now for this particular solution that we have here, okay, we need the n to be, it effectively comes out being a 3 now, because you, in order to get everything annihilated there, it's a 3. So what that means is you use all these terms, and the book starts out with C3s and C4s and C5s and C6s, but then they're going to lose them anyway, so let's just start with A, and if you'll notice what your terms are there, your alpha is still 0, your beta is still 1. So the first term there in the particular solution, coefficient capital A, that's what they've been calling it, that would be cosine x, your beta is 1, 2, okay, plus, goodness gracious, B times the x cosine x, okay. Now, that's because you've, the alpha, of course, is still 0, and the beta is 1, okay. And then you also have, and they did theirs in different order, it doesn't matter. Okay, sorry. I left off the X. Yeah. Okay, sorry about this. No. Okay. Now, let's back up a bit here. You have plus or minus I of multiplicity 3, okay? So your auxiliary equations have to have both the x term and the x squared terms, okay, in your solution. You don't need the first one because your function here you see you have a x cosine x and a so that's going to make your n equal, well, I'm sorry, the 3 here, the multiplicity of 3, that makes n equal 2. Okay, so you're going to have an x cosine x plus bx sine x, okay, plus c x squared cosine x plus d x squared sine x. Sign didn't write too well. Okay. Now, okay. This is just dealing with this equation right here. Okay? And that deals with this particular solution. I was starting to write down, now I see why they did it. You would have a cosine x and a sine x term in there, but since those are part of your characteristic equation, there's no reason to write those terms again. You've already got coefficients that are dealing with those, so leave those alone. They would have been written down here with the particular solution, but you can incorporate whatever you get down there in the characteristic solution. So you don't need to write those twice. That's why you can leave this out. You really needed 6 coefficients here because you have plus I minus I, and both are multiplicity of 3. That would have given you 6, but 2 of those can be absorbed by your constants you can't get rid of anyway. So that leaves this just being your particular solution. All right? So now we have to plug this back into our original solution, and that would be, and I may not have room to do it all, but let's try. I'm going to take this off of there so it won't be in the way. So let's see if we can get these done. Before you get the y double prime, you have to have y prime. I'm going to need more room, but let's try it. Well, yeah. Let me get more room. No way this is going to work with just what we got here. Oh, my eraser isn't picking up. There it goes. Yeah. Okay. Hopefully we can eliminate these. We've already dealt with that. And we've already done this. And yeah. And that. Hopefully we've already done that. Okay. We've already messed with all this. We'll just leave our characteristics equation, which has incorporated 2 of our constants already, leaving us 4. I can't get this to erase well. Okay? We've already done all that. Okay. And this. I can't get it to erase. Okay. I probably should have just started over. This is erasing so slowly. Okay. I think we got it down to the bare bones now. All right. I need to put my y double prime back in here. And it looks like I still have some smudge here. Let's see if I can get rid of it. Yeah, got rid of that. Okay. Sorry about that. All right. Now, let's do y particular prime. Okay. I know this is going to take a while and some space, so I wanted to allow for that. So we could call that A cosine x, product rule, plus, it's going to be a minus, a x sine x, because derivative of cosine is minus sine. So that's the derivative of the first term, plus, don't do the same thing here, b sine x plus bx cosine x, because derivative of sine is a positive cosine. Next, plus 2cx cosine x, have to wait for my pen to catch up, minus cx squared sine x. Okay? Still got the d to go, so I'm going to have to drop down a line. Plus 2dx sine x plus dx squared cosine. This is so aggravating. Cosine x. All right, there's my particular solution. First derivative. Okay. Now, is there anything here we can combine? All right. There's no cosine only term except this one. So a cosine x. That's going to stay the same. Okay. Now here we have an x sine x. And here we have an x sine x. Okay? So let's combine those two. I'm going to do plus 2d minus a x sine x. Okay. That combines these two. Already taking care of that one. Okay, we have a sine only here, so we'll just do plus b sine x. What a pain in the neck this is. Okay, and then we have an x cosine x, these two. Okay, so it's going to be plus b plus 2c x cosine x. That's gracious. Okay. And then we have our x squared terms, and can't do anything with them. Minus c x squared sine x plus d x squared cosine x. Okay, there's your y prime. Simplest I can make it. Let's do y double prime, yp double prime. Well, this is going to be a minus a sine x. Yuck. Okay. Let me go on and get this one with it. Plus b cosine x. Swear, this thing is such a pain. All right. Now this is going to have two terms with it. Let's just start with the one we've got. Plus 2d minus a sine x. Okay. Plus 2d minus a, sorry, okay, x cosine x. Man. Okay. That takes care of the two terms from that one. We've already done that one. So we took care of that one. The two terms from this one. The one term from that one. Okay. Let's do that next one now. That's going to be, we'll start with a plus b plus 2c cosine x. Okay. Yuck. All right. Now do the second term from there. There's the first term. Second term from there is going to be a minus b plus 2c. That's gracious. X sine x. Okay. Now I've got two terms from here. I didn't start far enough. Yuck. This is the second term from there. First one here, let's do a minus 2cx sine of x. Okay. Minus 2c x squared cosine x. Yuck, yuck. Okay. That's the two terms from that one. That one and that one. Now, I didn't allow enough room, so I'm going to go back in front here and do the first term here plus 2dx cosine x. Have to wait till it catches up. Minus dx squared sine x. Okay. Yeah. Okay. Now let's go back and isolate just the simplest terms we can. Sine x. You have a minus a here and a 2d minus a there. And those are only sine x terms. Okay. So that's going to be 2d minus 2a sine x. Okay, that takes that one and that one. Okay, the cosine x terms. That's going to be a 2b plus 2c times cosine x plus 2b plus 2c cosine x. This is such a pain. Okay, those are those two terms. That's that one and that one. All right, now the x cosine x terms. That's going to be this one and this one. These two together. So that's going to be a 4d minus a, looks like, I hope I did it right, plus 4d minus a. Now I'm beginning to regret something here. I used the capital letter D, which we have been reserving for operators, differential operators, not here. This is a constant D, okay? You had 2d minus a plus 2d, so that's 4d minus a, x cosine x. Swear. All right. That's those two combined. I swear this is so obstinate today. All right. Now we have x sine x. Okay? These are these two right here next to each other. That's a minus b minus 4c x sine x. So how's the best way to do that? A minus, let's just pull the minus on out front, and it's going to be b plus 2c, because the minus is out front. B plus 2c x cosine x. No, x sine x. Okay. Okay. And then we have our last two terms, which are our x squared. And they're both negatives. And something looks fishy on at least one of them. Yeah, that's, let me, something I think is amiss on one of those. Let me see if I can narrow it down and see. I think this is just a cx squared here, not 2c. Because it came from that term, and that was minus cx squared sine x. Yeah. Okay. So let's just write them down. Minus d x squared sine x. Goodness gracious. Minus c x squared cosine x. Yeah, I think we got them all in there now. All right. Now, we don't need the y prime p anymore because it's not showing up anymore. So I'm going to eliminate it here because I'm just running out of room. I hope I haven't made any mistakes because it won't be possible to go back and trace them down. And the eraser is incredibly slow right now. But the pen's been that slow for a long time. Oh no. All right. Sorry. I don't know why it did that. All right. Whew. Now, let's write what we just did with our particular solutions, the y double prime, which we have down here. And by the way, I hate to do this, but I'm going to. Let's get rid of this next part too. This was also our y prime. Like I said, I'm going to keep that complementary solution there because it will be part of our final answer. The y primes are not part of the final answer, so I'm going to get away with that. If I can get them to erase. There we go, finally. The y double prime is part, but I want that in the expression below, not this one here. This one had extra terms in it. If we combine those like terms down below. Going to keep the y prime because we need it. Partly of this is so I can have room, and the other part is so I don't look up and copy it from the wrong line. Okay, So this is now y double prime. I think I'm just going yp double prime. I'll take it off there and write it in here. Yp double prime is that. All right. So combining those together, yp double prime up here is going to be, this is a pain, but I'm going to write it again, 2d minus 2a sine x plus 2b plus 2c cosine x plus 4d minus a x cosine x minus b plus 2c x sine x. No? Okay. Going to continue on the next line. Minus d, minus d x squared sine x minus c x squared cosine x. Okay. Add to that y particular, yp, and this is plus ax cosine x plus, I knew that was going to happen, plus bx sine x plus cx squared cosine x plus d x squared sine x. Okay. Now that's supposed to equal this thing up here. X cosine x minus cosine x. Okay. Now for that to be the case, I'm just going to start writing some things down. Okay. I'll write them down in just about any order. Okay. There is no sine x. Wait. We need to combine our... Okay. We know that from here, 2d minus 2a is equal to 0. Okay, because there is no sine x term up above. Okay? Well, what does that tell us? A is equal to D. All right, that's done. Looking at the next one, 2b plus 2c is equal to a minus 1, because that's your, let's just make sure there's no cosine only. No, there isn't. So that's equal to minus 1. Doesn't tell us much there, but we can go with it. Okay. Next, we have 4d minus a we're looking at x cosine x plus a. Okay, when you combine this one and this one, you lose an a. So it's just 4d. No. This is such a pain in the neck. There we go. All right. 4d is equal to Goodness gracious. That's the x cosine x. 4d is equal to 1. All right. So d is equal to 1/4. D is equal to 1 over 4, which means A is equal to 1 over 4 because A is equal to D. All right, we got those two. So we took care of this one, these two. Okay. Then we have let's look at the x sign. Here we have minus b minus 2c plus b. So the b's go out, so you have minus 2c is equal to 0. Which implies, of course, that c is equal to 0. And if c is equal to 0, that's equal to 0, and you got b is equal to minus 1/2. Goodness gracious. Okay. Wow. Okay. And we got that from this one and that one. All right. Let's see if the rest makes sense. Okay. Here's a d. Oh, look at that. Dx squared sine x minus dx minus plus. Those go away, and minus cx squared cosine x plus. So they go away. Yes, we've got them licked. Okay. So, what is our final solution? Y is equal to the arbitrary solution, the complementary solution part, C1 cosine x plus C2 sine x. Goodness gracious. All right. Plus a particular solution. Your A was 1/4 plus 1/4 x cosine x minus 1/2 x sine x. C is 0, so we don't even write that down. D is plus 1/4 plus 1/4 x squared sine x. I wrote it in the wrong place. Sorry about this. Plus 1/4 x squared sine x. All right, let me take this off here so you won't be any more confused than you have to be. Well, I say I could take it off. It's being obstinate. Okay. There is your solution. Let's see how they did, and sure hope it comes out being right. Okay. Now they had different letters in it, but they wound up with y is equal to C1 cosine x plus C2 sine x, yes, plus 1/4 x cosine x minus 1/2 x sine x plus 1/4 x squared sine x, yes. Wow. Okay, that took how many screens by the time I erased everything I did. These aren't particularly quick. Now, I do want to remind you, I'll just, and this is, y'all wanted to do it this way, and I want you to see it every way. But remember, 4.4 was undetermined coefficient by the superposition approach. it says take your pick. You can either do the superposition approach, which we did in 4.4, or the annihilator approach, which we're doing in 4.5. So you don't need to do them both. But I wanted to show you both of them, or at least you expressed an interest in seeing both of them, so that you could pick which one you wanted to do. Frankly, I think the superposition came out a little cleaner, but that's my thought. I'll let you make your own decision. Let's move on then, and I don't have any way to check time. Let me see. All right, let's go to example 6. Determine the form of a particular solution for y double prime minus 2y prime plus y is equal to 10 e to the minus 2x cosine x. Okay. Now, and again, I never know how much of this I ought to write down, but I feel like this is important. Y is equal to e to the mx. Remember, that's where you're starting. Okay? The first thing you do on the left in the complementary solution, okay, is m squared minus 2m plus 1. Set that equal to 0. Okay? Well, that's obviously going to be an m minus 1 squared is equal to 0. So basically, m equal 1 is a double root, multiplicity of 2. And that's going to give you your complementary solution. And remember how we did that. That was yc, okay, is equal to c1, this is such a pain in the neck, e to the mx plus c2 x e to the mx. Okay, that's our complementary solution. Okay, let me clean that up a little bit, because I do, well, part I didn't want to erase, erased, and part I didn't. Okay. Yuck! This is such a pain in the neck. Okay, this is y sub c. All right, that's the first part. You can go back and check on that. You'll see that is indeed the case. All right, but they're actually just asking for determine the form of a particular solution for this. 10, don't worry about the 10, okay? What we concern ourselves with is e to the minus 2x cosine x, okay? Now, if you go back to page 150, example 7, equation 7, you see the annihilator, differential operator annihilates, that we have here annihilates these. Now in this case, our alpha is a minus 2. So jot that down. Alpha is equal to negative 2. Okay? Our beta here is 1. Beta is 1. Oops. Okay. Now with that in mind, and by the way, what is your n? Your n is your 1 more than the exponent for your x. Well, your exponent for x, there is no x here, so that's 0, so your n is 1. So that makes your annihilator here, for this side, to be d squared minus, I'll make that plus 4 because it's 2 alpha, minus 2 alpha, but alpha is minus 2. So plus 4 d and plus, and then your alpha squared is 4 plus beta squared is 1, so that's going to be plus 5. All right. That's your differential operator that's going to do your annihilating for you. Okay. So what you're going to do, you're going to take this and operate on, and by the way, in the text you'll see the complementary function for the given equation is y sub c is equal to c1. Oh, I left my m in there. M is 1. X, sorry about that. Okay. C1 e to the x plus C2 x e to the x. And that's what they got. So those are done. And then we found out our alpha is equal to negative 2, our beta is equal to 1, n is equal to 1. I guess I should write that down too. N is equal to 1. You probably should list all three of them. Okay. Now, from what we had up above, we would have we would know this annihilator operating on the right-hand side, okay, should give us 0. That's why we did it, okay? So this thing here, operating on 10 e to the minus 2x cosine x, should give us 0, okay? So let's apply that operator to the entire differential equation that we have here. Okay. Now, these are all going to be operating on y. Okay. So that gives you, and it doesn't matter which, they usually start with this, d2 plus 4d plus 5, that operator with n equal 1, okay, times your operator that you had here, that's a d2 minus 2d plus 1, okay? So these two things, product of those two series of operators operating on y should equal 0. Okay? Now you treat these as if they were polynomials. They're not, obviously. Okay? But let's do it. That would be d4. Okay, that should be those two. Minus 2d cubed plus 4d cubed. That's going to be plus 2d cubed. Saw that? Okay. Now our d squared terms. Plus 5d squared plus 1d squared. So that's plus 6d squared. Now our d terms. Okay. Those are only, one more d squared term. Sorry about that. One more d squared term, and that's this. Minus 6d squared. No, minus 8d squared. So that's going to make this a minus 2d squared. Sorry about that. I'm skipping steps just because I need to. I don't need any more room than I have. Okay. Reviewing that again, you only have one d4 term. You have two d cubed terms. This one and that one. Okay. d squared terms, you have your d squared. Okay, maybe okay. This is a plus 1d squared plus 5d squared, that's plus 6d squared, and your other d squared term comes here, minus 8d squared, that's minus 2d squared, I think. Let me go back and check again. 1d squared plus 5d squared is 6d squared, minus 8d squared, that would be minus 2d squared. Okay, finally. The d terms, okay? Here's a d term, minus 10d, and here's another one, plus 4d. That would be minus 6d. And now we're down to the constant term, and that's plus 5. Okay, all operating on y is equal to 0. Okay, go back to pre-cal, okay? How do you determine roots for something like this? Well, several things you can do. First, let's start with Descartes' rule of signs. You have 1, 2, or 0, positive real root. Okay? And then if you did the negative d, that would still be d fourth minus 2d cubed minus 2d squared plus 6d plus 5 equals 0. Look at that one. You have 1, 2, 2 or 0 negative real roots. Okay? Now, I'm going to take that one out just because I don't need it anymore. We've done it. We've got the number of real roots. 2 are 0 positive, 2 are 0 negative. Okay. Next thing I would do is rational zeros test. All your possible zeros are going to be plus or minus 1, plus or minus 5 over plus or minus 1. So that's plus or minus 1. Okay, let's see if a plus 1 is going to work. Let's just add our coefficients here. 1 plus 2 is 3, well, 2 minus 2 is 0. 1 plus 5 is 6, minus 6 is 0. Yes, that's going to work. So 1 is going to be a root, okay? We know that. Let's see what else we got. 1, synthetic division. 2, negative 6, 5. Okay, skip a line, draw a line. 1, 1, 3, 3, 1, 1, negative 5, 0. Okay, yeah, we knew 1 was going to work. Let's see if 1 is another root. Well, sure enough it is. If you add those together, you get 5 minus 5 is 0, so 1 will work again. Skip a line, draw a line, bring down a 1, 1, 4, 4. And by the way, these are our 2 positive real roots right there. You got 1, you had to have a second one. It's 1 and 1, a double root there. Okay? This will be a 5, this will be a 5, and that will be a 0. Okay. So your remaining quadratic is x squared plus 4x plus 5. That looks familiar, doesn't it? Okay? In fact, why did I do all that? I didn't have to multiply all those together. Oh, how stupid of me. We could have factored this. It won't factor. Okay? And factored this, and you had d minus 1 squared. There's our 2 positive 1 roots there. And this one will not factor at all. So you have to use quadratic formula. And I put x, they really are d's, but let's go back to d. d is equal to minus 4 plus or minus the square root of 16 minus 4 times 5. So this is, and that's basically all over 2. So this will be minus 4 plus or minus 16 minus 20 is a minus 4. So that would be 2I over 2. So this will be minus 2 plus or minus I. Okay. So those are your ones. A double root of 1 and a 2 complex roots, minus 2 plus I and minus 2 minus I. Okay. Now, from there, and by the way, you'll see that's what they got to, minus 2 minus I, minus 2 plus I, 1 and 1. Okay? Now, those ones there would give us roots of just because it's been so long since we did it, if you go back to I guess it doesn't. That would be 1 in X, okay? So without worrying about the complementary solution, I'm going to call this, for lack of anything, Y particular solution prime, okay? The ones there would be, and we've already gone over. Yuck! I'm going to stop. And note here, we're saying so close to finishing here. We're at this stage right here. We're picking up there. We got those roots of the auxiliary equation. Now, that's what they call it when you're dealing with the D's there. Okay. And those, well, we'll pick up that next time. Sorry, ran over. I'm going to end this.